Welcome back. In this segment, we're going to talk about the sequence of creating an add-on instruction. What are the steps? When you write code, besides writing the logic, you also have to define tags. You have to create tags and define them. So for an add-on instructions, what would be a logical sequence to do this in? In the software, there's a category, add-on instructions. This is in the controller organizer. If you right-click on add-on instructions, you get several choices. However, we're only interested in new add-on instruction. So I'll select it, and you're going to see this pop up. This is the basic information for an add-on instruction. You are going to have to type in a name. You're going to have to choose the language that you want to write the code in, and you can add some extended text to the revision level if you like. Type in your vendor name if you want, if you have one, and then click OK. If you were doing this in RSLogix5000 at this point, something else would pop up at this point. We're going to divert our attention away from RSLogix5000. In a later presentation, we will actually go through the complete process of creating this add-on instruction in RSLogix5000. But right now, we're speaking strictly conceptually. So here we have the frame for an add-on instruction. The components of an add-on instruction are the local tags, which are accessible only by the code in the add-on instruction. These tags cannot be seen or accessed outside of the add-on instruction. The parameters, which are the data ports in and out of the instruction. The parameters are configured as input, output, or as in-out parameters. So you see that the parameters overlap between the add-on instruction and the outside world. Do you remember what sets these parameter designations apart? That's correct. Some are by reference, referring to a tag in the general tag population, or by value. And last but not least, the code which is the entire purpose of the add-on instruction. Now let's back up one step. If this code that you already have written and tested, which it really should be, you can go ahead and create your local tags, then copy and paste the code into the add-on instruction. If you entered your local tags correctly and they match your code, it's probably a done deal. Or, like I normally do, I either write the code from notes in memory, or I paste it in and define the tags and parameters as I go along. So I kind of write the code and define the tags and parameters as I go. Use nothing in your tag names or parameters that is specific to the application that you are going to use the add-on instruction in. If you put too much description and lengthy tag names into your add-on instruction, and then you try to reuse this instruction in another piece of code or in another entirely different project, the tag names that you gave may contradict your application. So keep all your tag names and parameters as generic as possible. The name of the game here is encapsulation, object-oriented programming. You're going to encapsulate both the database, the local tags, and the methods, the code, into an object. When the instruction is executed, the code reads from the local tags and the parameters. The parameters are actually data ports within the program that this instruction is used, as well as controller tags that all tasks can access. So these input, output, and in-out parameters are going to access program tags from which this add-on instruction is being used in, and they can also access controller tags that are available to all programs in all tasks. In review, one more time, input parameters are passed by value and not by a tag reference, as well as the output parameters. The input parameters and output parameters passed by value, they are synchronous and will not change during the execution of the add-on instruction, whereas the in-out parameters are passed by reference. You will have to make the decision when you create your add-on instruction whether to specify your parameters as input and output or as in-out type. You could just make them all input and output, but remember that input and output parameters execute slower and require more memory space. That is one of the complaints about add-on instructions for programmers that have heavy memory usage, is that the input and output parameters, which don't change during execution, actually use more memory and take more they take more time to execute. Welcome to the next section on add-on instructions. In this section, we're going to go over the anatomy of an add-on instruction. So, how does an add-on instruction come into existence? What actually inspires us to create an add-on instruction? Well, we grow weary of rewriting the same code over and over again, and we finally encapsulate it into a reusable format. So, we need to pick an application that you can use over and over again. First, you need the application. You need a plausible situation where creating an add-on instruction makes sense. The initial investment to write the code, test it, and document it will be an investment with no immediate return. However, the sacrifice, once made, is in the bank to draw interest off every time you create an instance of that add-on instruction in any and all future projects. For years. Okay, so we're going to pick something real simple here. In the industrial controls world, there are many things to control. One of them is motion. And the simplest is two-position, back and forth, in and out, insert and remove type motion. Simple two-position motion. This is normally accomplished with a pneumatic cylinder. There's a piston inside of this cylinder that can travel back and forth, and the cylinder has a port at each end. In the picture you can't see the ports, but they're there. Take a closer look at this photo. There are two sensors attached to the cylinder, one at each end of travel. They sense the position of the piston inside the cylinder. Each of the sensors has a status LED. If this status LED is illuminated, the sensor has sensed that the piston is at that end of the cylinder, or you could say in that position. In some applications, the piston doesn't actually travel all the way to the end of stroke because the rod, which you see sticking out the front there, is attached to tooling, and the tooling runs into a hard stop, and that is the position that you want. So you actually adjust the sensor to sense that it's where you want it to be at the end of that stroke. The sensors are installed in the correct location to sense the piston at each end of the cylinder. Take note that the status LEDs now represent the piston retracted. If you look close, you see one of them is illuminated and the other one is not. Let's apply compressed air at one end of the cylinder. The piston is forced forward and the cylinder is now extended. Notice also that the status LEDs have changed state. Now we apply compressed air to the opposite end of the cylinder and the piston is forced back into the cylinder into the retracted position. Notice that the status LEDs reflect the retracted position. We are going to revisit these two sensors later on in this presentation, so please remember them. How do we control the compressed air to apply it to one end of the cylinder and then the other to get the back and forth extend retract motion that we need for our machine? We use a pneumatic valve, the position of which is controlled by two solenoids. On each end of that valve body you see a solenoid and you see electrical elbow connectors. Inside of that valve body is a spool. It's a long rod with concentric grooves machined into it, and as the spool shifts back and forth, it connects the ports from one side of the valve body to the other to allow air pressure to flow in the direction that we want. Remember that a solenoid is a coil of wire that when we pass electrical current through, and as the free electrons race through the loops of the coil, their individual magnetic fields all join together to produce a powerful magnetic field that can pull a ferromagnetic material such as iron. It is this principle that we operate this valve with. Each coil gives you direction control of the compressed air. So what would the electrical circuit look like to operate this valve? This is where the rubber meets the road, folks. Here we go. This section of the presentation may seem a little out of place. However, we want to make sure that everyone watching these videos fully understands the process that the add-on instruction we're going to create actually demonstrates. What you are looking at is an electrical ladder diagram, not a relay logic ladder diagram. The left and the right vertical lines are the power rails that supply the voltage to these three individual circuits. These three individual circuits that you see connected between the power rails are totally independent of each other electrically, but not logically. The contact relay 1CR connects these three individual circuits logically. The relay logic here uses the normally open contact of 1CR to energize solenoid 1, which shifts the spool in the pneumatic valve to switch the pressure to the rear of the piston to extend the cylinder, and vice versa. The normally closed contact of 1CR energizes the second solenoid, which shifts the spool in the pneumatic valve in the other direction and puts air pressure on the front of the piston and pulls the rod back inside the cylinder to retract it. So normally open extends it, normally open, normally closed retracts it, as shown on the print. Let's consider some questions about the electrical relay control diagram in front of you, just to make sure you understand the process. Are there any devices currently energized? Now remember, you have three circuits going from, well, left to right, right to left, and they're across the voltage. So you're looking for a complete path for current flow to energize a load. Correct. The second solenoid is energized by way of the normally closed contact 1CR-2 because 1CR is de-energized. And the normal state of a contact is based on when the relay is de-energized. So it is normally closed, therefore there is a path for current flow through the second solenoid, and that actually holds the cylinder in the retract position by way of the solenoid valve. Are any of the contacts in this diagram right now true? In other words, without pushing the push button 1PB, how many or are there any true contacts in this diagram? Remember, you have true if on, true if off. So we're using that terminology because that's what we use in PLCs. So a normally closed symbol is true if off. In other words, it's true for current to flow through it if the relay is off, so true if off. So 1CR-2 is true if the relay is off. 1CR-1 is true if the relay is on. The push button, you could say, is in its normal state, it's normally open. Therefore, when you push it, then it becomes true and has current flow. So, are any contacts currently true? Yes. 1CR-2, true if off. Are there any false? Yes, 1PB, could because it's not being pushed, and 1CR-1. They're both false. If we press the push button and hold it down, are any devices energized? Correct. 1CR contact relay is energized, and the solenoid 1, which extends the cylinder, is energized. Are any of the contacts true? Push button 1 and 1CR-1 are true. 1CR-1 is true because the relay is on. Therefore, the contact is closed. Are any of the contacts false? 1CR-2 is false because it is true if the relay is off. Therefore, since 1CR is energized, then that contact is false. It is very important to make note that the contact 1PB is an external device and part of the process. In this case, the operator interface, probably on the door of a control panel, is where that push button is located. In contrast, electrical relay 1CR and its associated contacts are internal to the logic of the control system. Remember this point, it is going to be very important. This is an electrical relay ladder diagram. The left and the right vertical lines are power rails, as we explained. They supply voltage to the three individual circuits, and again, they are totally independent of each other electrically, but not logically. The contact relay 1CR connects these three individual circuits together logically. All three of the individual circuits can be separated each into two sections. So we're talking about three separate circuits here, and we can separate each of these three into two sections. In the section to the right are what we call actions. In this case, we want the control system to energize one of the two solenoids to extend and or retract the cylinder by way of a push button. Energizing the coil of contact relay 1CR is also an action, but it is an internal and intermediate action that does not directly cause any change in the process or machine that we are controlling. Now, it's in the path from the push button to the solenoids, but it's internal, not external. The push button's external and the solenoids are external, but the relay is internal. The remaining section would be the conditions or permissives. We have two categories of objects, actions and conditions. And in each of those categories, we have two classifications. We have external and we have internal. This is important to remember. You have external devices that bring information into the relay panel. The operator pushed the button requesting the cylinder to extend. You have the relay logic that decides how and when to extend, retract the cylinder, and you have solenoids that electromagnetically operate the pneumatic valves that meter compressed air to the cylinder. We are really getting close to transitioning now back to logic for a PLC. So we have external and we have internal. You might say that the external devices are parameters by value, and the internals are local tags. So keep this concept in mind when we get a little further and add on instructions. The push button is an input parameter. The solenoids are output parameters by value. And the internals, the contact relay, is a local tag. This concludes this segment. We're not stopping here because we're done with the subject, but the little alarm you heard going off in the background, that kind of ended the session at 20 minutes. So we're working on a goal to get to around 15 minutes per segment. The next segment, we're going to actually start doing some logic for the cylinder with RSLogix5000. Now, we're not going to use the software on the screen. I'm just going to show you the logic and explain how it functions, and eventually we will encapsulate it. So we'll see you in the next segment. Thank you.